Hello, good afternoon, friends. We welcome you all to today's webinar on ECU extract. We'll hold on for some more time before all of other members join, and we'll start at 3 o'clock.
Thanks, Karthik.
Good afternoon once again. Let's hold on for a couple of minutes. We'll just start the webinar exactly at 3:02 p.m. Bhishma, am I audible?
Yes, Karthik, you are audible.
Good afternoon, everyone. I welcome you all to another webinar of ANSET. So today's webinar, we will be focusing on ECU extract. So quick introduction about ANSET. ANSET has been a tooling and engineering service company for automotive and aerospace for almost 14 years. We build our custom products in verification and validation as well as in AUTOSAR and other tools. We also do custom tool development for our clients in various verification and validation and development services. We do a lot of training services in VNV, AUTOSAR and other things, and we also offer consulting services in this area. And myself, I'm Karthik, 16 years of experience in product development, focused more towards RF system design and automotive electronics. So this is a quick background about us and our organization. So let's dwell into the webinar. So what is the motto of the webinar? All right, so whenever you want to start building an ECU, let's say assume that you are a tier 1 company and you want to start building an ECU, there are two components. There are majorly two areas that you will build. You can be an application development engineer, or you could be like say a BSW stack engineer. So either way, what happens is an OEM will provide you with something called as an ECU extract. So our objective of this webinar is to help you understand what this ECU extract is, how will it be useful for a tier 1 company to understand this ECU extract, and how it will be able to help you build the ECU. That is one thing. That's the first thing, helping you understand what the ECU extract is all about and where it sits in the whole AUTOSAR methodology. That will be the first objective. And the second objective is we will help you kind of understand to do one ECU extract actually help you do it for one module. So this is something that we will focus on today's webinar. I'm joined by my colleague Bhishma and Manzoor, who will also help us take this through. All right, like I said, the first objective of our webinar will be to help you understand how what is an ECU extract is, what is the role of the ECU extract, and the second is we will help you do an ECU extract in RTOP. Before we go into the quick introduction about AUTOSAR, for all the newcomers, I recommend you to go to our previous webinars to understand what AUTOSAR is. We have discussed a lot of, we have done a lot of webinars on AUTOSAR architecture and various other topics. On a quick note, the whole objective of AUTOSAR is to, whenever you develop application software from a previous perspective or a legacy standard, what happens is the whole application software was completely dependent on the microcontroller and the ECU, the hardware unit, right? So that was the major disadvantage of the electronic control units that were developed in legacy methodology. It just had three layers. It had like say an application layer, it had a CAN driver or whatever driver, and then it had a CAN stack, and then you had the whole excuse me, and you had the microcontroller. So what happens is the whole application was dependent on the microcontroller, and any change in the hardware unit with the advancement of a new microcontroller or a new ECU by any of the semiconductor industries, what happened is this whole electronic control unit had to be removed out. So that is where AUTOSAR came into picture, where the whole objective was to separate the application software component from the hardware component. So whenever there is a new hardware replaced with a few minor adjustments, the same application software component can be integrated into the new hardware and tested, and still the robustness of the application can be still maintained. So this is the whole objective with which AUTOSAR was dwelled. And I'll just give you one quick the layers. Okay, so in the AUTOSAR layered architecture, there are actually three layers. We have primarily the application layer, which is focused here, and then we have the runtime environment, which is the RT layer, and the whole gambit of layers that you see in violet, green, and orange together is called the BSW stack, the basic software stack. All right, and then we have the finally the microcontroller, which sits at the bottom, the physical unit below which you will have the transceiver unit and the bus, and so and so forth. All right, so the whole objective of today's session is to kind of help you build this one layer. Okay, the home COM module. We will not be focusing on the whole. Uh-oh. Can you hear me, Bhishma?
Yes, Karthik, it's clear.
Yeah. Okay. So one reason for why our focus will be is to help you understand how do we build a communication stack from top to bottom, and we will show you how we can do it in this this violet layer. There is for the first module, which is the COM module. We'll help you do it in that layer alone. So that's the whole idea in which we will be focusing on. Okay. So this is the whole AUTOSAR methodology that we are talking about, and this comes from more of a tools perspective. The whole object showcase is done in a tools perspective, so it's easy for all of us to understand, especially when we are using tools. All right, the first layer is the software description. So whenever you want to develop a software description or you're working on an application layer, you will need this SW description from the application layer. All right, or you from the tier 1 company. So only if you have this software component description, you will be able to generate the code for this ASWC. We have done a detailed description of how to create an ARXML file based on a requirement for the CTETR application. You can refer our previous webinars on that. And with the ASWC software component ARXML file. All right, so when an XML file is generated for an AUTOSAR standard, it's called an ARXML file. That ARXML file you can import into tools like, say, for example, MATLAB, or you could actually import it into tools like Vector, generate the whole, develop the whole skeletal of the software structure, and then you can actually do the logical implementation using, like, say, tools like Simulink, or you could do C coding for that and generate the .c and .h file. So this will actually help you generate the whole storyboard for application software component, and you can actually have the .c and .h file ready for use, right? The second important thing the OEM has to do is the OEM has to have the system description. So in the system description, what happens is it is something similar to our DBC file, which we use in our legacy methodology. So in the DBC file, it actually contains the signals and descriptions, signals and messages of the entire network. Say, for example, a car may be built with hundreds of ECU, or like, say, if it has 20 ECUs, for instance, a low-end car. So this system description will contain the messages and signals that is actually required for transmission between all the 20 ECUs. That's the high-level detailed plan which will be available. And this also we have done on webinar, where we have told you how to do a system description file. And the third part is the ECU description. So in the ECU description, it will be focusing exclusively on one particular ECU. Let us say, for example, you as a tier 1 company is developing a software, both application software and a BSW stack for a CTETR application. Let's put that CTETR application. All right. So the signals and messages that will be available only for your ECU will be provided to you, the tier 1 company. The details of the other ECUs may not be available with you. The only signals and signals and messages that will be required for your ECU will be provided to you, and that is actually called the ECU extract. So this is the whole ECU extract. And when you load this ECU extract into a Vector DaVinci configurator or a EB Tresors or any other tool for that, there are, like, say, Oven Systems, they've got a BSW stack. So many people have got a BSW stack, or Tata Elxsi has got one stack. So what you do that, it will actually generate all these configurations. Like, say, you will have an RTE configuration, the OS configuration, the BSW configuration, the ECU abstract. All these configurations will get loaded. So there are so many modules that are required. When you load your ECU extract into that particular configurator, what happens is only those modules that are required for your application will be picked up and they will be loaded in your BSW stack. All right, so that will be available. And once you have that, the next step is actually going on to configure your requirement. Like say, for example, the COM module that we may be talking about, you will have to configure the COM module for a particular requirement. So you will go ahead and choose what you need to configure so that you can actually generate your BSW, right? And for your RTE, you may go and configure your RTE for that particular application so that you will be able to generate your RTE. And you will have to configure the OS, like say you will have to choose the task, you will have to assign buffers, you will have to give resources, and you may choose a single core or a multi-core OS. All those things have to be done, and finally you generate a .c and .h file, which you compile and which you compile with your application software component, and finally you build your ECU extract, or I'm sorry, you build your ECU file, which is fused into the ECU. So this is the whole storyboard. But if you look at what we are focusing today, is we are focusing exclusively on the ECU extract. So what do we mean by an ECU extract? ECU extract is a small is an extended version of your system description file, where it contains details of all that is required to build your ECU. That's it. So you will contain the signals and messages that are built for your ECU. It will contain what are the modules that will be required for building your ECU. It will contain how these modules are going to communicate. It might contain what are the IPDUs or what are the IDs in which it has to be transmitted. How do you configure those fellows? What will be the destination address? All those details will be provided by your ECU extract. So once you load this ECU extract into your BSW configurator or whatever tool that you are using in your organization, the ECU extract will actually pick up, the configurator will pick up all the modules that are required for your ECU development. And then you can actually configure these modules, whether it's RTE, OS, BSW, ECU, and finally integrate it with your application and go for the build. So this is the whole ECU abstract that will be generated as the part of this whole process. All right. So like we mentioned, the system extract is more of a complete network information, where it contains about the details of all the signals and messages that are part of the network. But an ECU extract is something that contains details of the atomic software components, the runnables, the modules of the BSW, the system signals of the BSW, the IPDUs, and how these signals will be transmitted from the application layer to the BSW stack. All those information will be provided in your ECU extract. All right. So a well-defined if you're working in a Tier 1 company, you usually get two things. One, you get your ECU extract. The second, you also get a separate document from the Tier 1 company which specifies what are the modules that needs to be configured for the requirement of the Tier 1 company, so that it is compiled and it can be tested. So you get both these documents. One is the actual extract, and second is the configuration. All right. So a typical ECU extract should have details of the selection of the basic software modules. Like I said, if you talk about the communication stack alone, like you can refer our previous webinar on communication stack to understand what are the modules that are associated with the communication stack. So if you look at the communication stack, there are like modules like the COM module. There are modules like say the PDU router, the CAN TP, the CAN IF, and you will have the CAN drivers and the CAN transceiver. All right, so you will actually have details about all these software modules for the communication stack alone. And for the IO stack, again, you will actually choose, like say, for example, your CTETR application, you may use a PWM, you may use some digital IO devices. All those details will be available. Similarly, you will have details about all your configuration, your MCAL as well as OS. When I say the OS is usually the AutoSAR OS, which comes as an integrated part of the BSW configurator. So you will have to configure the details of the task and map it to the runnables. All right. It could be both ASWC runnables, or it could be like, say, for example, BSW components as well. So you will have to map it to all these components and schedule these components for execution, right? All this information will be available there. And there will be, like, say, integration of complex device drivers. Usually what happens is the integration of complex device drivers comes as a separate module where the AUTOSAR engineer is actually required to kind of build the CDD. Usually they build their own protocols. In CDD, they don't use the protocols that are associated with the standard automotive, like, say, for example, they don't use CAN or FlexRay. They build their own protocol standards in the CDD. So it comes as a separate sheet. This is more of our experience. I'm not very sure others could have different options as well. But in our experience, we found that CDD usually comes as a separate sheet where we are required to build our own protocol stack and integrate it with it. So a complex device driver is usually a fellow which is when you want to build something which is not part of the AUTOSAR stack, then you bring it as part of the CDD. But the CDD also needs to be integrated with other BSW modules like the OS and other fellows as well. So that is the whole. So the output, if you look at the target will be the AUTOSAR basic software module, which is the .c and .h file, which will be compiled and through your compiler, and you will have to set your debugging. So this is the whole objective. So what we are going to see today is, I think this is pretty much from the theoretical aspect. So what we want to run you through is, we want to kind of showcase to you one small ECU extract that we have built for built. All right. And we will actually show you how an application software component ASWC is built. We have actually done one separate webinar on that. You can refer our ASWC. So here, in this particular webinar, what we will do is we will take the first layer, which is the COM module here, and we will see how this mapping, that means how the data actually flows from the application layer to the COM module. We will talk about implementation, we will talk about system mapping, and we will talk about how this data flow happens, so you have a very clear understanding. And once you load this, like, say, as we mentioned, if you load this ECU extract into your DaVinci configurator or any other stack, like, say, EB Trezor or whatever stack it is, then what happens is it will pick up, the stack will actually pick up all the modules that are required for configuring this particular application or BSW, and you can start working from it. So that's how this works. So if you look at it from a COM stack perspective, because we are focusing more of the COM stack, I thought we will just showcase to you, like, say, how this COM stack is going to work with, right? So the signal which is coming from you here on top of the RTE, you will have the application layer. Okay, so let us assume I have one application software component. Let's call it EX. From the application software component, the data comes out of this application software component to the COM module, and it comes as signals. All right, it's called system signals. All right, so this system signal will be transmitted from the application software component to the COM module through the RTE. All right, so the ECU extract will have complete detail about how this mapping of application software component is done with the COM module. So that is what we are going to focus on. And once you have this done, the next step is actually moving this COM module into this data from this AUTOSAR COM module to the PDU router, and from the PDU router it can be actually routed to the CAN interface, or here if you look at it, it can be routed to the CAN interface, or it can be routed to the CAN TP if it is a CAN packet which is greater than 8 byte. Then it can actually be transmitted to the CAN TP, and which does the segmentation and reassembly, and then finally it moves to the CAN interface, which is then forwarded to the CAN driver, and so on and so forth. All right, so the whole flow works like that. So from the application software component, the data flows into the COM module through the signals, and from the signal it flows to the PDU router. From the PDU router it could go to the CAN interface, CAN driver, and so on. All right. So AutoSAR uses, okay, we will show you the ECU extract, but generally AutoSAR uses two simple methodologies to kind of help each module understand this flow. There are two things. Are one is it uses a there is a system buffer which is created. So the data is actually collected from the system buffer. So we actually have pointers to refer the system buffer from which the memory the data is being picked up, and there are something called as handle IDs. So these handle IDs are assumed by different modules. COM module will give its own handle ID to pick this data from the ASWC. PDU will have a different ID to kind of pick the data from the COM module. The CAN TP can have a different ID to pick the data from the PDU router. Sometimes what happens is the CAN handle ID can remain the same. The handle IDs can actually remain the same. For example, CAN TP could use the handle ID 5. Similarly, PDO router can also look at take the handle ID as 5, but it does not make any difference because to transfer the data from the COM module to the PDO router, it uses a separate set of API, and this API will have a different definition. So it will be usually like say COM underscore PDU transmitter underscore PDU and whatever data you want to transmit. So the ID will be one part of it. Here when it transmits from PDU to CAN, it will be PDU underscore CAN. So even if both these flows have the same ID, based upon the API, you can still differentiate it. So like I mentioned, pointers are used to help the data traverse through different modules. And second, different modules use different handle IDs to transfer the data. So this is how it is actually. Let's say assume that in the C code, that's actually how it is. It will look like using pointers and IDs. Now we will use a tool like say RTOP, and we will actually showcase to you like say how data flows from the application layer to the COM module. We will limit our scope of discussion only from application layer to COM module. Like say the procedure for transmission from COM module to PDU router remains the same. So you can like say you may not use a you may not use a CAN, you may use a FlexRay. In that case, you will use from the PDU router, you will use it to FlexRay and you will transmit it. So based on your requirement, this will go forward. But generally, the procedure remains the same. So I will stop here, and I will request my colleague Mansoor to show you a quick demo on how to do this routing between the application software component and the COM module. Mansoor?
Yeah, hi Karthik. Is my voice is clear?
Yeah, you're loud and audible. Yes, Mansoor.
Okay, sure. Let me share the screen. Okay, hi all. Very good afternoon, and hope my screen is visible.
Yeah, it's visible. Yeah, it's visible. Yeah.
Okay, perfect. So here, this is our one of the sample ECU we created with 3 ASWC and what other service layers also, BSW, COM manager, ECUM, and IO hardware and OS. So we have these three ASWCs and these service layers already available. We'll assume that we have all these three things, like all these things like we have currently with us. Now we need to create an ECU extract for this particular ECU. So how we going to start is that, like, first we need to create a root composition with this ASWC. So as whenever Karthik was showing, like we'll have multiple ASWCs inside one application component or application layer. So inside that application layer, we'll group the ASWCs to be into one single root composition, and we'll keep all these things inside it. So that root composition. So for that is the first step to create an ECU extract. So we'll group all those. So grouping, like you can create a separate ARXML for that, and you can create a root composition. So here new child and AR package we will be creating. Sorry, like here root composition, it's already there. That's why it's not showing the option to create it. You can create a new this thing like root composition over here, like in the downlink, this thing composition software component. So this will be like we'll create a root composition, and inside these root compositions we need to create each prototypes. we need to create prototypes for all the components, whatever we have to be kept inside this composition. So we'll be creating a prototype for BSW module, COM module, seatbelt SWC module, ECUC, and our mirror handlings. So if you see, like, we have mirror manager, seatbelt, and telltale. So these telltale SWC and all those things. And one other interesting aspect we need to see over here is that the multiple instance, if you wanted to create here, whenever we are creating our ASWC, we'll be creating one model of it, which includes the ports and their internal behaviors and all those things, and the data types corresponding to that particular ports and all. But if you wanted to implement this mirror manager for multiple instance for right and left, let's say if you wanted to implement this seat belt for right and left, then what we could do is, like, here in this root compositions, whenever we are creating package, we can create multiple instance. So we'll be creating the multiple individual package for all the components to be kept inside this composition. So I'll just show you one thing here. One I'm just taking one as an example, one SWC. I'm just giving one short name, and here type, I can actually choose what is my this thing, air root seatbelt or air root application software component. So here in our previously available SWC mirror management, I'll be having this application software component type. So I'm creating a prototype for this application software component. If I wanted to create create a prototype for seat belt, I have this seat belt over here. So in my seat belt, where is my seat belt? Here it is. I have just given driver seat belt. Here I'll be choosing my type as this seat belt. So totally what's happening here, I am creating a prototype of this particular ASWC into my composition. So I have taken all my components, service component as well as application level components into this. Now we need to decide, do we really want to communicate all of these signals or all of these port data to the outside ECU? In between ECUs, like, we will be communicating with the ports, S ports, R ports, and everything that we have detailedly discussed on the application level, a webinar on this application software component development. Here we are more focused to speak on the data which is to be transferred to the COM stack, which is to be transferred to the other ECU. So now we'll create a separate ports to this root composition, which are all needed to communicate outside that ECU. So for that, this is our root composition, which is having all these components. Now I am creating these ports. I have one out value to be sent out of this ECU, and I am expecting one other port. This is also out only. See, if I have certain values to be fetched back, that is also we can create over here. So likewise here in my application or in my system or in my ECU, I have two values to be like put outside to this ECU, or I need to transfer that two values to ComStack. So I'll create these two ports. This is the next step. Now whenever I create these ports, definitely we know whenever I create a port, I need to mention the interface of that port, what data types it will transfer, what how many arguments it will have, or what are all the values we'll be passing through that. So to make this port, we need to define an interface. So let's go to another ARXML file where I have defined the interface for this root composition. So in this, I have this interface. Here I have two interfaces. One is that belt check interface, and the other one is mirror M interface. So in this belt check interface, I have this status. This is my one argument only I'm passing. This is my status, and this data, some, if I wanted to define the property of this particular data, I can go ahead and implement. So here I have mentioned this is status. Now it's not only just mentioning what data we will be passing or what variable data prototype we are passing. We need to mention what data type we will be passing. So we'll be having implementation data type and our application level data type. So in this argument I mentioned, I'll be using belt status data type. So here I have defined what is belt status data type. So this belt status data type, here I'll have it, and this implementation data type is also I have created. And inside this mapping, I will be doing my belt status data type into implementation data type mapping. So here I have done mapping. So if I choose this status for this particular interface, it means in the implementation level, definitely they're going to choose this implementation data type. Where we can,
మెట్లు మరి నేను అవా చెప్పులంగి 4 అన్నారు కదా 4
yeah,
అన్నారా
okay. So here I have mentioned the implementation level. I suppose someone is unmuted.
అవును అంట మా అమ్మ కూడా
Yeah. Okay. Hope it's clear. Okay. So in the implementation data type, I have mentioned Boolean is the final data type. Implementation level, C level data type is Boolean. Now we'll be using this data type name to map to the exact microcontroller level knowledge, level data type. Like if it is a char, or if we are using some CPP, there will be Boolean or something, or depends on that. So that is like here, from here we'll take downward to the microcontroller level. So this is how I have mapped my data type. I have created my interface same way. Like in mirror management, I have a mirror message which internally using this int type. In that int type is mapped with int implementation type, whereas int implementation type is a value. I have just given it as a value, name as value. We need to define this or typed up this value to corresponding, maybe uint 16 or uint 8 or whatever according to the need. So likewise, so I have this interface currently in my hand. Now I'll be using the corresponding interface which is defined for my data types and all those things. So I'll be using that interface over here in this port. So I'm using mirror M interface for this, and this port will be using belt check interface. So I have chosen what interface I need to communicate with. This is again a port for root composition. Now we have a port in the root composition. Now we need to decide upon, okay, from what ASWC I need to feed the data to this particular port, which is to be shared to the outside of the ECU. For that, we'll be creating some delegate connectors where which speak about like how to communicate this ASWC port to the root composition ports. So here in this delegate connector, I'm taking as outer port is mirror val RX port output, which is root composition. And I'm just giving the short name for this particular delegate connectors. And in R port, I'll be mentioning, okay, in this base, inside this root composition, I have a left mirror SWC prototype, which is nothing but this. So this is actually in turn back, go back to the ASWC over here. This thing ASWC mirror management, this ASWC, it will be mapping to that. And they are saying it is a left instance. It's not like, it's not a right or this thing. It's a left instance. And this left instance mirror position port, target port. So if you see over here, no mirror manager, I have a mirror position port inside this. So it is actually saying just connect this root composition port with left mirror SWC prototypes mirror position port. So we are actually mapping an ASWC port of the particular instance to the outer port. So if you have two instances and you wanted to send both the instance, you create two ports over here and you map what instance, what prototype you need to choose. Maybe right, you have right mirror, then you create one more delegate connector, and inside this you choose right. Here you will be getting all this instance. So you choose right, so you'll get the right. So it will go to right instance of that mirror and it will take the value from that R port. So you will get that. So now we have what we did in a short, we have created a outer layer, outer box, which includes all the SWCs and service and all those things. And we created ports to communicate to the downstairs, to the down com stack. And we mapped the ASWC port with the outer layer port using a delegate connector. This is what we have done. Now we have these road compositions done and we have these ports. Now the next part is that I need to map it. I need to map so that like it will be converted into IPDU and all those things. So for that, I'll be needing some signals. So what I'll do for that purpose, I'll create some signals, I signals and all those things. So I'll just create a system signal. As Karthik was mentioning, I'll be needing certain signals to communicate, some system signals to communicate. So I will just create two system signals for my purpose. One is belt val RX message and mirror val RX message. So I'll create two system signals and then I'll map these system signals to I signals. So here in I signals, if you go, see these system signals I mapped. Now these I signals are mapped with my system signals and these I signals are again mapped to IPDU. So if I go to IPDU, this is my IPDU and that IPDU is mapped with this I signal is this I signal. So now if you see, I have a system signal that is mapped to the I signal, which is mapped to the IPDU. IPDU will be the messages like IPDU, I signals and all those things will be the messages going to the COM stack. We'll have system signals in the ECU extract levels. So I have a ECU extract level signal also, system signal also created. I have the ports also created in the root compositions. Now the ECU extract plays the role. Means now I need to map all those things to an ECU extract format. So I'll go to ECU extract. So basically in ECU extract, I'll just minimize the rest of the thing so it will not confuse. Okay, so in the ECU extract, I'll have 1, 2. That is implementation mapping of the components and the signal mapping. These two are the main role of ECU extract. So now implementation mapping, I need to map all of my ECUs to their implementations. So whenever we create any components, like whenever we create, maybe like I'll take one ASWC for our easy understanding. I'm taking mirror management. So I'm just going to mirror management and my name is software to implementation mapping. And here component implementation, I'll be able to see mirror manager ASWC implementation. Where we'll get this? In this mirror manager, I'll be having this implementation created. Whenever I create an ASWC, I will be having this implementation created, like what programming language, what is their behaviors, hardware elements, and all those things will be defined. Here, like for our demo purpose, like we didn't completely filled it, but we can fill all these behaviors. So the complete implementation of the ASWC will be there. So this implementation, which is available for each ASWCs as well as services, we need to actually map it to the ECU extract. So here I am doing my implementation mapping over here, like ECUM component, software C for BSW, I'll map it. For mirror management, I'll map it. I'll map the component as well as like the target component is what composition as well inside the composition. So for that, like I'll include my root software composition also. So this root software compositions I have included into ECU extract, and inside that, here whenever I am saying I am mapping my implementation of mirror management, I'll say, okay, this is of this particular prototype, left mirror, this is of left instance, this is of right instance, you can see it, right instance, right instance I'm creating. So here I can actually choose it, like from here I can choose it. So this way I can map it, my mirror management ASWC implementation, to the component word composition. So this is like implementation mapping. So here to the ECU extract level, to the whole ECU, what is the implementation defined in the ASWC is mapped to the root composition and which is mapped to the ECU extract. So this is what is happening in this ECU extract. So I wanted to map all these ASWC or all the service layer components. So I'll be mapping all this. Now, once I have done this, so I have done ECUM, IO hardware, software component to BSWC, and my mirror management, COM implementations, and the other rest of the ASWCs, seat belt, and all those things. Now, once this is done, once the implementation to software component or software component to implementation mapping is done, I can do signal mapping. You must have remember, okay, I have a system signal created. Now I need to map it to the port. So I will just take sender receiver to signal mapping. See, I hope like we are all clear about how to create these subcells and all those things. We have discussed like this before in our previous lessons. It's like same thing, like some new child, and I can go to the corresponding module data mapping or whatever. I can choose whatever is needed. Here we are not actually going and navigating through all this like in an assumptions, like we are already discussed it in the previous webinars. So here like in the signal mapping, what I can do, I can choose a sender receiver to signal mapping, as I'll be using a sender receiver port in my root composition. I have used that one. So here I will just choose my system signal is this, whatever we have created inside these signals. So here we have created our signals. So that signal I'll choose, and inside this, I will mention that, okay, in this ECU extract, inside this composition, this port mapped with this particular system signal. So whatever the data target prototype is this mirror message. This is the data prototype. Whenever we say this port, we know that in the interface, inside this thing, this is the mirror interface was the interface used. This is the data prototype I need to communicate. So here we are saying in this port, this particular data type, you just map with this particular system signal. Now that data type, whatever the data getting over here will be mapped with this system signal, which is mapped to I signals over here, and which is again mapped to IPD over here. So now let's, if we quickly go back and see the flow, how it is, my ASWC, like our scope of discussion was completely like from ASWC, one data to be transferred till COM. So if I see like I have a data over here, I have a data in this particular port of ASWC. Here I have my interface seat belt status. Now or like whatever this value or whatever, like if it is something else or this thing mirror status or whatever. So here I have it this port, I have that data from the ASWC, its name is mirror person or something. Now this data will be mapped down to the root composition port using delegate connector. That's first step. Now this delegate connector have this port, and they are having an interface with the data type implementation and what are all the data types. So here I have converted that into, we were speaking about mirror. So it's like mirror message. Now I have this data. The data came from this point through a delegate connector. I got it into this format with this implementation level. So now I have mirror message. Now this mirror message is part of root composition. That root composition data mirror message, using my ECU extract, I am mapping my signal to system signal. This mirror message of this particular port in this composition, I am mapping to this system signal. Now this system signal is mapped to I signal over here. Here this, sorry, here it is like mirror this thing. So I signal mirror val RX message, this system signal is mapped to the I signal of this thing. Now this I signal is mapped with the IPD over here. So it's all the way from the ASWC port. I have my data traversed to the root compositions, and I to the delegate connector, it came to the root composition port, and that root composition port is mapped to the to a system signal using system extract, and then that system signal is like mapped with an I signal, then to the IPDU. So I hope the flow of the this thing data communication is clear from this one basic example or one basic ECU extract of an ECU. Yeah, that's all I wanted to share as part of this simulation or the tool from the RTOP perspective. Yeah.
Oh, thanks, Manzoor. Any questions? We would like to pick it up. So once you configure this
Hello.
ARXML and yeah, sorry.
Hello.
Yeah.
Yes, just one question. In the signals, I mean, we have this I signal, IPDU signals.
Correct.
Why do we need so many stuff? Like, why cannot have only one? And like, why we need IPDU? Why we need IPDU signals or system signals separately?
All right. So,
yeah.
all right. So it's actually just one signal. There is no multiple signals per se. If you look at it, okay. Can you see my screen?
Yes,
So,
I can see. Yes.
No,
Yeah,
no.
I can
Manzoor,
see.
can you just stop sharing? All right. Can you see the screen now?
Yes.
Yeah. So there is actually not many signals like what we presume. There's only one signal. Let's say, for example, you have this application software component here, right?
Yeah.
Okay, let me assume that he is going to start one simple signal, signal he wants to transmit. Let's say, for example, that signal is called seat status. Okay, what is the status? It's a Boolean variable that he wants to transmit. Let's assume it that way. Okay. So this Boolean variable will take only one single bit. Am I right? And that has to be transferred from the application software component to your ECU, which is like say sitting in the lowest layer, right? So what happens is this Boolean variable will be transmitted from here to the communication module. So when it is actually transmitted from here, it is just called signal. All right. So you do that implementation mapping. So it is called as a signal. And in this communication module, what happens is you need to, this data has to be transferred, right? It has to be transferred to the PDU router. So what happens is you add headers there. You had a header, all right. So if you add the header will actually tell you what is the pointer information. So the data is actually not transferred. Actually, the data is actually put in one memory location. So this COM module is actually will point to that pointer. So that pointer, and it will add one handle ID. All right. So that handle ID tells you that this is coming from the COM module, and it is also pointing to this pointer. So this information is passed to this PDU, right? So once it comes to this PDU router will again look into that pointer location. From that memory location, he will go read it. He will add his own handle ID and transfer it to the, let us say, for example, CAN interface. All right. So there he will add in that PDU router, he's adding another ID, right? So he is called IPDU. And then next is like say CAN interface. So here in the CAN interface, he will add his own ID and he will transmit it. So if you look at what is actually being transmitted, it is just that Boolean variable which is actually transmitted from top to bottom. What gets added is these headers. All right. So with that signal you get added, it's called IPDU. Here you add, in this header, it's a COM module header. This is like say a PDU router header. Here you will add another CAN IF header. So it's just the headers that gets being added. And when it comes out of the RTE for a differentiation purpose, it's called as a system signal. In this whole BSW stack, like say here in this this is actually in the services layer. Here it is called as a NPDU, and once it goes into this interface layer, it is called as an LPDU. Here it is actually in the network layer. That's why it's called IPDU. And after the CAN protocol, it's called. and then here it is LPDU and driver. Why these names is just to differentiate. Okay, see what happens is still the PDU router, the data does not even know that whether it is going to be transmitted to a CAN packet or it is going to be a FlexSpray packet or any other packet. All right, only in the CAN PDU router, excuse me, or in the CAN TP, what happens is you actually convert it into a CAN packet. So that is where it actually becomes network dependent, and that's why it's called NPDU. All right, so primarily what it means is I'm adding a CAN header. Got it. So the different names are only because you add different levels of header. Just like your OSI model, where you like say one layer you add your TCP address, the next layer you add your network IP address, the next layer you add your hardware address, and you transmit. And every layer it is called physical layer, all those things. It's the same storyboard here. It's just the header gets added, but the data remains the same. Did I answer your question?
And that header, yes, and that header will be same for one ECU extract, right? It's static, or it will change.
It will change.
For one signal.
For every signal, it will change.
Yes, but for one signal, it will be same for one ECU extract.
For one ECU, correct. For one signal, it will remain the same. Okay. For n signals, you may have n headers, but for one signal, it will remain the same. Correct.
Okay, thank you.
Sorry, for me, it didn't answer the question why. Why is it that AutoZAR specifies to change the header in each location?
Okay, see, what happens is the whole objective of AutoZAR is if you take the legacy ECU, all right, you will just have 3 layers. You will have the application software component. The next layer is the CAN stack. So what happens is, or whatever protocol stack you have it. So once the data comes out of the application layer, it will actually you will add the CAN signal to it. All right. And then the next step is you will pass it to the CAN driver, where you will actually, like say, once the CAN driver, you will map it to the hardware. It's a pretty straightforward mechanism. Application layer data comes, you add the CAN header, then you just send the, what happens is what do you call, send it to the CAN driver and send it to the microcontroller. It's a pretty straightforward mechanism. But here in AutoZAR, the whole objective is to create a layered architecture, so that today, let us assume that I have the application here. Today I want to transmit it to a CAN through a CAN signal. Tomorrow I may move the same application to be transmitted to a FlexRay, right? So here it comes as a signal. When I transmit the application layer, when it comes from here, it's coming as a signal. Let's assume the next step is for me to convert it into a CAN signal. Then what will happen is this whole data has to be changed. This whole process has to be changed. But now I don't have to do it. All I have to do is in the PDU router, I will create a new static table. That static table, when I get this signal, instead of routing it to my CAN TP, I will route it to my FlexRay TP. Just that header there is going to change. So all the process above will remain the same, correct? That's the whole idea.
Yeah, so the simple explanation is independence between layers. So there is no, what do you say, there should be no, the
data should be independent of the layers, correct?
So that's the whole point of AutoZAR.
Correct.
But in terms of traceability for ASPICE, that's going to cause an issue, right? I mean, or how do you create traceability for ASPICE in this case?
So the tool will actually take care of the traceability issue. So we don't have to worry about it. All right. So the tool, when you load this data into the tool, all right. So the tool will actually take care of the whole traceability issues.
Okay. So it will generate a traceability report. Is that correct?
Yeah. It will generate the whole report.
Okay. Thank you.
Yeah.
Thanks, Karthik. So I just have one follow-up question. Maybe.
Sure.
So what you mentioned is like in the whole process, it's a pointer that is being transmitted, right? The one starting from the interface, like the Boolean variable we took. So it is basically a pointer to that variable which got transmitted throughout.
Correct. Pointer variable with there will be like a handle also to it.
Adding the handle. And like the other guy mentioned like I signals. So these are I signals are these signals, right? Which are
correct.
Basically communicating with the sender receiver interface through some buffers, right?
Correct.
And IPDU also he mentioned, like, but why IPDUs are required? Because IPDUs are only required after COM as per this picture. So why he mentioned IPDUs?
The COM module is actually like say it has both the ends, right? So it will like say receive and transmit, correct?
Yes. Yes.
So that's why.
So it can transmit. Okay. It can write back also.
Yeah. There will be a callback function also, correct?
Okay.
That's the reason.
Understood.
Can I ask one more question? Sorry.
Sure, please.
So from the PDU router, when you're talking about the different protocols, is that the basic OSEC type of communication in that case? So we are going back to the legacy definitions, are we? Or
From the PDU router?
to, like, let's say CAN driver or FlexRay, is it following AutoSAR?
It follows AutoSAR, including the microcontroller which sits in the lower layer, which is not part of this picture, has to follow AutoSAR standard.
Yeah, okay.
The drivers are also having AutoSAR standard. Like say the CAN driver in legacy will be a little different. I don't say altogether different, but it will definitely be a little different from the whole AutoSAR architecture. Yeah.
So, and the data pointer remains the same. It's the same location through the layers. Is that right? Or is that transferred?
Yes. It depends. Okay, see, usually what happens is even for the PD router per se, what happens is the PD router does not, or let's say, for example, the CAN TP, that's a pretty good example what we could take. If you look at the CAN TP, where it is responsible for segmentation and reassembly, it does not have an internal buffer. All right, it uses the same buffer which is on top and kind of creates a signal and transmits it. So that way what happens is we don't overload the system. If you want to, like say, do it in a way that it is a little different, there are options that are available where you can actually create a container at a different location, but this is a usual procedure that followed in AutoSAR. But you can create your own container. There is an option for it.
Is any of the like spin lock or any of these things related to this data at all?
Sorry, I didn't understand the question.
Like spin lock or any sort of lock status for comms. Is that related to any of these signals? Like waiting or what to say, like the 4 different states you have, like ready, wait, and what do you say, ready, wait.
Which module are we talking about?
In terms of the communication wise, when you're talking about prioritizing.
Okay.
Is it related to this COM?
I'm actually not very sure about this prioritize. Like say what question it is, but the prioritization is definitely part of the COM module. All right. So in terms of execution, it as like say execution is part of the what do you call OS, right? So there you can actually map it to the execution and like say give it a higher priority and transmit if that's what is the question.
So to avoid deadlocks,
okay,
communication. So normally you have like spin lock and things like that. So there are different states. Where is
okay.
Yeah.
Okay. So see that part of the configuration, you will actually have to include that as part of your code. Okay, see what happens is AutoSAR provides something called as an integration code. All right, so all these things which are not part of the standard of AutoSAR, you can actually have something called as an integration code where you can actually write the whole sequence of code. Let's say for example on this particular condition you want to create a sequence of code that can actually be written, that logic can be written. That option is being provided to the user to do it.
Understood. part of the specification.
Yeah.
I thought something IPDU multiplexer is doing something there. I'm not sure what.
See, multiplexer is actually not doing that job, actually. To my knowledge, at least.
Right. So IPDU multiplexer is what you mentioned about dividing it into.
No, I was talking about the CAN-TP. CAN-TP was responsible for segmentation and reassembly, especially when you have data packets more than 8 bytes, and if it's a CAN signal, then CAN-TP is responsible for that segmentation and reassembly.
Is it the same for CAN-FD? The same?
Yeah.
Thanks for answering.
Yeah.
So when you are using DCM, that time only this CAN TPR will come into picture. For normal CAN, it's not necessary.
Not necessary, correct.
I have one point.
So in the normal CAN, the PDU router will actually push the data to the CAN interface directly. Yeah, sorry, please.
Yeah, Karthik. So this is Robin. So I do have one follow-up question. So
Sure.
What other information that we can fetch from ECU extract? Like basically, I understood like the messages and this concept you explained very well. I understood this is all related to like communication thing. But other than this communication, what else we can get in ECU extract?
Everything, like say for example, you can actually, if you have when you get a ECU extract from the OEM, it will have details about your IO hardware abstraction. It will have details about the mode management. It will have all the details for your diagnostic stack. Yeah.
Yeah,
Small point.
even the details like DTCs, what are the DTCs getting set and when they are getting set, like this sort of information also, DTC numbers, or we need to ask for something different for these things?
See, it usually depends upon, like say, who the OEM we are working with. See, sometimes an OEM will give you a requirement, like say, for example, I want to develop this particular processor, and you help me prepare the whole requirement from an AUTOSAR perspective. That could be one kind of an OEM. But for more OEMs, they will have a complete stack. They will give you a complete ECU extract. You just load the ECU extract, it will generate the whole stack. All right. And they'll also give you like a complete requirement, say, like say, for example, DTC lock, all those details, they will give it to you. So you'll have to just do it per se, as per their requirement. That's another way of doing it. So it primarily varies from which company gives you that requirement. There are a few young age organizations which will just give you like a requirement in terms of what they want to solve from an application perspective. The rest of it, they will ask you to help you build the requirement with them. So that is also another type of organizations.
Yeah. Karthik, just one more question.
Sure.
For example, I am a application software developer and I am writing algorithm, let's say, to detect something. And so those algorithm will be also part of ECU extract or not, like C code.
What happens is, like say, for example, if you are an application software component developer, see, I'll just go back.
Or only the interface will be.
It will have only the interface. It will only have the interface. Correct. It will have only the interface. So here is where you will actually. This is what you will require from an application software component perspective. All right. So this is what you will have. Okay. So this is like, say, for example, you will have. How do you call the RTE layer? So this RTE and the contract phase will actually generate all the headers in the files, like say APIs, on how you will reach out to the RTE layer. All those information is, and your scope of work will usually be restricted only to this, because if you pass the data successfully to the RTE layer and you are able to kind of debug that and say that it is successfully transmitted to the RTE layer, it is the work of the BSW stack engineer to kind of pull it from there.
Yeah. So it means that we will have only interface information for the algorithm.
Correct. You will have only the interface information. Exactly.
And then inside the interface, that you need to use those interface and you need to write the algorithm and
Yes,
but in the
yes.
ECU extract will not have those C code, whatever
No,
you can
it
write
won't have. It won't
algorithm.
have. It will not
Okay.
have. Yeah.
Okay. Thank you.
Karthik, one doubt.
Sure.
Actually, what this ECU extract is only for the application software components that are split across multiple ECUs, or when the OEM
No,
is
ECU
preparing-
extract is for actually developing the BSW stack for one particular ECU.
Okay. But if the communication is inside the ECU itself, it's not communicating with outside ECU. Also, ECU extract come into picture.
ECU, then it has no problem. Actually, if it is inside that ECU, then it usually you may use the IO hardware abstraction or something like that, right? So you'll only use the IO layers. If you are going to have an inter-ECU communication, then you'll have a delegation port which will actually tell that this data is not coming from this ECU, it is going to come from another ECU. So there you use something called as a delegation port.
But what my question was like, if I get ECU extract for one ECU like ECU1,
Okay.
that means it gives only the details of its communication outside with outside ECUs, or with inside ECU also it will give the information.
It will give all the information. Inside ECU,
Inside
intra
ECU,
ECU.
how the OEM will be knowing when they're preparing the ECU extract?
See, from the application software component, let us assume that you are, like, say, for example, writing for that particular ECU, you have, like, say, 4 application software components. Let's assume that way. Okay. So
Okay.
you will so in that case, so what happens is you will actually pass the data only to the RT layer. One moment. So here, let's say, for example, if you have 4 application software components, 1, 2, 3, and 4, you will actually push the data here, and from here you will read the data. It's pretty straightforward. All right. But if you, let's say, for example, say, for example, you will have to kind of control, let's say, for example, you'll have to, simple use cases, like, say, you'll have to, it's a cluster issue and you want to kind of display some telltale, right? Then you will have to access the IO hardware, right? That detail will be provided by the ECU extract. So he will tell you, like, say, for this application software component, this message has to be linked to the IO hardware, and it will drive this flow, and it will have to drive this telltale. Say, for example, seat status telltale, whether a seat belt is worn or not. That telltale has to be, like, say, displayed. He will give you that information, and he will give you this whole storyboard from here to here, like, say, how it has to flow, what message, what signal, and all this stuff.
Okay. If it is below RT layer, this comes into picture.
He will give you an ASWC also with like, say, for example, like, say, ECU extract, like you mentioned, it is for below the RT layer, correct?
Understood. Thank you, Karthik.
Karthik, can I ask one question?
Sure, sure.
So after ECU system extract, we will get the IO abstract XML file. So do we need to configure this as part of BSW configurator for the ECU, or it will be already configured?
It will actually be configured, like, say, for example, what Manzoor has done, right? If you look at what Manzoor has shown, if you actually configure it that way, it is actually configured. The BSU configurator, you don't have to configure anything. It will be ready for production, actually.
Okay. So if any change, we can configure by using
that change will actually be given as a separate sheet.
Okay, thank
you. See, usually during version changes, they would have already configured. So they would have wanted some change that they will give it to you in an Excel sheet or something like that. So there you can need to configure the change. I think thank you so much for your time. It was quite an interactive and interesting session. So if you have any questions, please do write to us. And the next Thursday, I'm sorry, the first, we usually have it on every first Thursday, but unfortunately we had some prior commitments. We couldn't do this first Thursday of every month. So our next webinar will be on the April 1st, the first Thursday of April, and it will be on AutoSAR diagnostic stack. So let's connect together again on April 1st. Looking forward to see you all. Have a nice month. Thank you.
And we are going to get recording of this one, right?
Yeah, it will be. We'll give you the recording. Yes.
Okay. Thank you so much.
But Karthik, last session recording was not available. About I think.
Yeah, that one I will re-upload because we need some editing on that.
Okay, I was searching for it. Couldn't find it.
Those are RT, right? I will re-upload that. That will be tomorrow.
Yeah. Thanks.
Is it available on websites?
Yeah, it is on our YouTube channel. It will be like say Ansett YouTube channel. You will find all our webinars, and we like say we also have an AutoSAR community, learning community in LinkedIn. There we also kind of share all these details.
Thank you.
Thank you.
Sorry, Karthik, just a quick question.
Sure,
So
sure.
RT and hypervisor, they both have no difference in this context?
OS and hypervisor, isn't it?
Yeah, sorry. So in case of using hypervisor, there is no difference.
No, there's no difference. Yeah.
All right. Thank you.
Usually use hypervisors when you have like say high-end processors, which are like say you have an IDC, you use an hypervisor, right? Infotainment systems and all those things. But usually our cases we use OS only. Most of the applications.
All right. But the syntax and all remains the same.
Remains the same. It remains same. Yes, it remains intact. Yes.
So hypervisor will mainly be basically interacting in hardware, right? So it will be more implemented in hardware.
Correct.
Okay.
Thank you.
Thank you. Bye-bye.
Thank you all.
Thank you.